Okay, here's a quick bonus video talking about how inconsistent systems and underdefined systems can appear within real-life contexts. So first of all, you can get an inconsistent system in scenarios where you're trying to achieve something that's not possible, perhaps as a result of having multiple goals that are actually incompatible or mutually exclusive. So, for example, suppose you're somebody who's trying to eat, reasonably healthy, right? But you're also somebody who has a lot of food sensitivities and is really only comfortable eating buttered noodles. So maybe your health goals for a day of eating are to eat, 40 grams of protein, pretty bare minimum amount of protein, eat maybe 20 grams of fiber, eat maybe 2,000 calories, somewhere around that. Can you achieve these health goals on a diet of buttered noodles? Let's check it out. Well, if you look at the nutrition in a 100-gram serving of butter, that 100-gram serving of butter contains just about 1 gram of protein, no grams of fiber at all, and 717 calories. If you look at the nutrition in noodles, 100 grams cooked, that contains about 5 grams of protein, about 1 gram of fiber, and about 137 calories. So if we let the variable x1 represent the number of servings of butter that you consume in a day, and you let the variable x2 represent the number of servings of noodles that you consume in a day, then this system would represent your goals. This first equation would represent your protein goals, and this would be zero point 0.9 times however many servings of butter you had, plus 4.5 times however many servings of noodles you had. You would want that sum to equal 40. The second equation would represent your fiber goals. So there's no fiber in the butter, so that would be 0 times x1, and then you would have 1.2 times x2, and you would like that to be 20. And then a third equation might represent your calorie goals. So 717 times the number of butter servings you consumed, and 137 times the number of noodle servings you consumed. And you would like that maybe to equal 2,000. But if you try to solve this system, you will find that there is no solution to this system. If you try and solve this second equation for x2 to figure out how many servings of noodles you would have to consume in order to meet your fiber needs, you would have to consume about 16.7 servings of noodles to meet your fiber goals. And so think about that. That would be like 1,600 grams of cooked noodles, which would be multiple pounds of noodles. And if you're eating multiple pounds of cooked noodles, we can already see that there's no way you're also going to be able to meet your calorie goals for the day. So this system of equations has no solution because the goals that you have set for yourself, trying to eat healthy on only buttered noodles, that is impossible. So this has given rise to an inconsistent system with no solutions. Now, by contrast, you can get an underdefined system, a system with infinite solutions, in a scenario where there are multiple viable ways to meet your goals. Imagine that you're trying to eat healthy, but you give yourself just a few more foods to choose from to build a healthy diet. For example, maybe you allow yourself to eat some combination of blueberries, avocado, tofu, chicken, and brown rice. Based on the nutritional information for these foods per 100 grams, if I let the variables x1 through x5 represent the number of servings of these foods that I consume in a day, then my goals for protein, for fiber, and for calories can be represented by this system. Now, in this system, I have 5 variables to choose from, but I only have 3 restrictions, which means that I actually end up with 2 free variables. representing that I have some choices and some wiggle room, some options in terms of how to meet these health goals. I can mix and match these five different foods in a couple of different ways to meet my health goals for the day. So this is an example of a system that has infinite solutions, a system with free variables, what we call an underdefined system, as it might arise in a real-world context. Underdefined systems represent that you can get your goals met in multiple viable ways. Another real-world scenario that gives rise to an underdefined system is when you're setting up a system, but you don't have enough information to solve for all the variables in the system. So, for example, maybe you're a transportation engineer and you're trying to study the traffic in a simple street network, like the one represented on this picture. Now, to measure traffic in a street network, you have to actually measure it, right? You might have actually seen on various streets the little device that they put up with the cord that stretches across the street that's used to measure traffic flow through that street. And that equipment costs money, setting it up costs money, taking it down costs money. So ideally, you would like to solve your traffic network using as few measurements as possible. So let's suppose that in this traffic network, we have measured the traffic coming out of 1, 2, 3, 4, 5, 6 one-way streets, and we're trying then to solve for the traffic on these other 1, 2, 3, 4, 5 streets in the network. Now, you can set up a system of equations representing this network by looking at every single intersection in the network. At every single intersection in the network, all the traffic that comes into that intersection eventually has to leave that intersection. So the total amount of traffic coming into any point of intersection must equal the total amount of traffic leaving and coming out of any intersection. So for example, at intersection A, we have 300 plus 500 traffic units coming into the junction. And we have x1 plus x2 units of traffic going out of the junction. So the flow in and the flow out must be equal, which gives us the equation 300 plus 500 equals x1 plus x2. If we examine the other four junctions in this network in the same way, we get in total four equations in the variables x1 through x5. Now, if you solve this system via method of elimination, for example, you end up with a free variable, reflecting the fact that we had five unknowns, but we only had four restrictions and four equations on those unknowns. We end up with a free variable. So this system has infinite solutions. And what that represents in this real world scenario is that we have not taken enough measurements to fully solve the traffic pattern in this network. It looks like we would need at least one more measurement to solve the traffic pattern. For example, we would need to measure the traffic going on this road here, represented by X5.